So expressing solution concentration. We have quantitative words that describe solution concentration. So a dilute solution has a small quantity of solute relative to the solvent, and a concentrated solution has large quantities. Those words are nice. They're not really useful in chemistry, but we've got concentrated and dilute. And then there's a whole bunch of different ways to quantitate the solution concentration. So some of these we are familiar with. Molarity, remember that one? We've used that a lot. Here the solute is measured in moles, and we divide it by the solution volume in liters. Here's a weird one that looks like a typo, but it's not. Molality. That's the amount of solute in moles again, but the mass of the solvent in kilograms. We'll talk about why you would even ever care about that. Mole fraction, mole percent, parts by mass. So parts by mass, this is where we get percent. So any of these are considered parts by mass. So you can have percent, you can have parts per million, parts per billion, parts per trillion, ppb, ppm. So if you get the water report from the city and it lists all the different things they've tested for, most of those things are listed in parts per million or parts per billion as the concentration in the drinking water. Here, what we're doing is we're taking the fraction, the mass of the solute divided by the mass of the solution. So, that's the theme of percent. It's the part divided by the whole times a factor. For percent, we're multiplying by 100. Parts per million, we're multiplying by 1,000,000. Parts per billion, multiplied by 1 billion. You can also have parts by volume, where you have volume of solute in solution. You can also have mass to volume, just to mix it all up. Why do we have so many? Because they are useful, they are convenient in different situations. Molarity is really convenient for chemists because we're often doing stoichiometry problems and we need to know how many moles of stuff is in there. But in most professions where they make solutions, they don't care how many moles are in there. They just need a number to slap on it, and something like parts by mass is going to be a lot easier to make the solution because you can just weigh the stuff and mix it together. So molarity, we've talked about this before, amount of solute divided by the volume of solution. The amount of solute, the number of moles in this solution does not change when you heat up the solution, but the volume of the solution will change a little bit when you heat up the solution. So molarity will change slightly with temperature. And it generally is going to decrease because water is less dense at higher temperatures. So that is the reason we have molality. So here, molality, we're looking at amount of solute per mass of solvent. The mass of solvent does not change with temperature. So molality is a unit that will be constant regardless of the temperature. This is abbreviated with an italicized lowercase m, not to be confused with meter, right? Or with the capital M, which is molarity, or any of those other M's we've run into, like milli, but milli by itself is just not really a thing. It has to be in front of some other unit. And the value of this will be really similar to the molarity, because molarity is volume of solution in liters. How much does a liter of water weigh? It weighs 1 kilogram. Because a liter is 1,000 milliliters. A kilogram is 1,000 grams. Density of water is 1 gram per milliliter. Parts by mass, parts by volume. We're looking at the ratio of the solute to the solution and then multiplying by a factor. And we've used percentages before. When we have a 14% by mass solution, what that means is 14 grams of solute per 100 grams of solution. And so that's a really good conversion factor for a problem that's asking you how much stuff is in there. Parts per million, parts per billion. So example, 15 parts per billion means 15 parts, 15 grams per billion parts. And so you could use grams here as the unit, you could use pounds, or any mass unit you want, because when you divide them, the units cancel out. Parts by volume, 22% ethanol by volume means 22 milliliters of ethanol in 100 milliliters of solution. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. So we've got some numbers here. And we have a question. What mass? And this is a problem that can be solved using dimensional analysis. So if I write down the things I've been given, I've got 355 milliliters. Now, in a solution, there are two parts, right? There's the solute and the solvent. So 355 milliliters, that's of the solution, right? That's the soft drink. That's 355 milliliters of solution. And we've got 11.5% by mass. Well, that means 11.5 grams per 100 grams. It's 11.5 grams of the sucrose. I'm just going to use the word, it's a little faster, in every 100 grams of the solution. We need to identify these or we're going to go sideways. And then we have a density, 1.04 grams per milliliter. Well, grams of what per milliliter of what? Density is mass over volume, yeah. So, but is this the density of sucrose or the density of water? It's the density of the solution. Okay, so they're saying assume a density of this. It's not super clear. They mean the soft drink has a density of 1.04. So that means that 1.04 grams of the solution occupies a volume of 1 milliliter. So both of these things that we're given are fractions or ratios or per units, right? This per that. 355 milliliters is just milliliters. So that can help us identify that this is the place where we're starting from, and these are going to be used as conversion factors. And what are we trying to find? We're trying to find grams of sucrose. Well, this is milliliters of solution. Any of these things have milliliters of solution? The density does. So that would allow me to convert from milliliters of solution to grams of solution. And then what does this one relate? Grams of sucrose and grams of solution. Well, I have grams of solution and I want to get grams of sucrose. So that's my factor here. So 355 milliliters. We got two factors, so we're going to have, or two arrows, so we're going to have two factors. We're going to grams of solution, so that's 1.04 grams per milliliter of solution. Those cancel out. And then we're going to grams of sucrose, and we're dividing by grams of solution. So 11.5 grams of sucrose to 100 grams. And those units cancel out. So 42.6 grams of sugar in a 12-ounce can of soda. Do you remember when we weighed out the 15 grams of table salt for that lab? The lab where we made the solutions and measured the densities, you had to graph it. 15 grams is a lot of stuff, right? 42 grams of sugar. That's a lot of sugar. Just trying to see if you're paying attention. Yeah. 42.5. Thank you. Any other questions? A water sample is found to contain the pollutant chlorobenzene, the concentration of 15 ppb by mass. What volume of this water contains 5.00 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1.00 grams per milliliter. So again, let's find the numbers that were given and the question that we're being asked. We want a volume of water. And then let's write these down. 15 parts per billion. Percent is parts per 100. So here, this is equal to 15. Generally, we use grams, so let's just use grams of chlorobenzene. I'm going to call him CB because I'm feeling lazy. Divided by a billion. A billion is 10 to the 9 grams of solution. This one's a little tricky because water is the solvent, but we're saying this is water that has this concentration in it. So I'm going to say solution. Then we've got 5.00 times 10 to the 2 milligrams of chlorobenzene. And we have a density. Oops. Oh, the whole thing's ugly. 1.00 grams of the solution per milliliter of a solution. So I'm trying to find volume of this solution. And I'm going to choose milliliters because I think it's just going to be easier than anything else. Do you see how this first one and the last one are probably conversion factors and not what we're starting with? I'm starting with the milligrams of chlorobenzene, and I'm trying to get to milliliters of solution. So from milligrams, if I look at these guys, I don't see milligrams anywhere. But could I convert milligrams to grams? Yeah, that would not be a problem. Well, now in this factor, we have grams of chlorobenzene to grams of solution. Grams of chlorobenzene can go to grams of the solution. And then this density allows us to convert grams of solution to milliliters of solution. So 5.00 times 10 to the 2 milligrams. We're going to grams. And we're going to go to so this is grams of chlorobenzene. And we're going to grams of the solution. And then we're going to go to milliliters of the solution, dividing by grams of the solution. So the units cancel out. If we don't specify grams of what here, it'd be super easy to get this in upside down, and then we're going to end up with a crazy answer. So milli means 10 to the minus 3. Grams of solution, that's 1 billion grams of solution contains 15 grams of chlorobenzene. And then our density, 1 gram of solution to 1 milliliter. So 5 times 10 to the 2 times 1 times 10 to the minus 3 times 1 times 10 to the 9th divided by 15 divided by 1. Gives me 3.3 repeating. So we could round that. Oh, I guess we only have 2 sig figs. So 3.3 times 10 to the 7th milliliters to get 500 milligrams of chlorobenzene. Any questions? So here the answer was given in liters. My answer was in milliliters. That's 4 trains so far during lecture.